Okay, so today we will study with the motion under gravity, and we are considering here fixed acceleration due to gravity. Okay, that means the amount of gravitational force is fixed here. Okay, and also we consider a very hypothetical situation that there is no air risk. Okay, for simplicity, we are assuming this thing. So one thing is clear: we are trying to study the motion of a single particle when there is only gravity interaction taking place. Okay, so one thing is very clear: this motion is definitely taking place in a vertical plane. That means in a plane which is perpendicular to the ground. Otherwise, this gravity has no effect and no question of any gravity if you consider in horizontal plane. Okay, right? Okay. So suppose you are standing here. What happens? You are standing here and you are throwing some particle. Okay, you are throwing means you are projecting. You are projecting with some velocity, right? If you are projecting with some velocity a particle, so suppose here from here the particle will what? Will do what? It will first rise a bit and then it will fall down. Okay, so why this is so? Because when you are projecting some velocity, it is starting with some velocity, so it will try to rise above, but it cannot rise on its own. It is always its rise is always hindered or checked via or due to the presence of gravity or gravitational pull, as you may say, which is pulling it downward. So what will happen? You are projecting it with some velocity. This velocity, due to this velocity, is trying to rise, but after some time, or rather we may say gradually with time, this velocity decreases. Ultimately, and this one, after reaching the maximum height, at this point, actually, the velocity vanishes, becomes zero. And then it again starts falling. That is, the gravity becomes the powerful one here. It falls under gravity on this place. So here, the velocity starts decreasing. That means here the velocity is positive. Now the velocity is decreasing. So it is negative, and at this point, it is zero. So what will happen? It will follow some path like this. So our point here is to find out, or rather you may see, or rather check, if this path or the trajectory will definitely be a parabola. Up to what assumption? Up to our assumption that this gravity is fixed, as I said, and there is no air resistance, or there is no other force. That means no air resistance means only I am just trying to mention that only gravitational pull is the acceleration to acceleration, main acceleration, or the other force you may say which is acting here. There is no other external force. Okay. So now let us see how we are going to get this situation. For the starting point, I am saying whenever you are not only for this problem, for any problem, what we will actually assume is suppose there is any point from which the particle is starting its journey. Okay, we usually, or rather for our problem, we consider this point as the origin and two mutually orthogonal axes passing through this point as our reference axis. Okay. Now, this is not mandatory. We have to consider that first point of the particle as this origin and this corresponding axis as the x and y axis. You may consider some other point also. But what will happen, as you will see, this is the most simplest expression we will get here. If we assume like this is the most simplest, we will get ourselves, we will achieve our goal most easily. If you consider any other point as your origin, other than the point from which it is projected, okay, then it is a bit of all these expressions will be a bit more complicated. Okay, so just to avoid that thing, unnecessary calculations we are considering not only for this problem, but as we will progress, we will see for many other different problems. Once we are saying, okay, there's some point from which it is starting its journey or some point of concern, we consider that as the origin. And correspondingly, two axes we draw through it mutually perpendicular and we consider them as the x and the y axis. And this is quite also matching with our vertical plane situation as we are saying. X-axis will be along the ground and y-axis will be perpendicular to the ground direction. Okay. So now let us see how they are deriving, or rather how they are framing the parabola trajectory, as we said. Okay. So one thing is clear, as you are just starting from here, it will have two acceleration. So suppose I may just say, let me draw this a bit more perpendicular. Okay. And as I said, my particle was initially here. It is now starting to move like this and have projected with some velocity, initial velocity u or something. Let me see whatever symbol they are using. I will go on carrying on with that symbol only. And what is happening at any point, you are just trying to fix the particle. So as soon as you are doing this, you are just breaking down into components. What? Its acceleration you can break down, its velocity you can break down. So we will first consider acceleration. Why? Because we will use the equation of motion. As we said, we will need to frame the equation of motion. So what is the thing if is happening here? As you can see, we have said before that there is only acceleration due to gravity. That is the gravitational force is the only force acting. So there is no force acting in this direction. Okay, so we can easily say this m d2 is m is the mass of the particle equals to 0. And one force is acting in the vertical direction, only one force. And what is that force? Perpendicular downside, G. Okay, that means y is increasing on the upper side and G is just the opposite direction. So what should we get? M d2y dt2 goes to minus. So this is your set of equation solution. Okay. Now we will go on simplifying carrying out our calculations starting from here. Okay. So I will not just go through how they are doing it from here instead of just directly finding them out. Okay. So as I said, all this writing corresponds to what I have said, whatever I have said, and P is any position at any time t. Any position means at any time t you are just trying to, as if you are considering a stationary position of the particle. And you are studying it, where it is, what is the value of x, what is the value of y, what is your vx, what is vy, like that. So as I said, these are the equations of motion. So from the first one, easily you can find out dx dt. Okay. Now see the initial condition. Initially, what? Initially means when you projected it. So when you projected it, that means at the point O, as per our assumption. Okay, you projected it with a velocity u, but this you can see this velocity here. Okay, so the component of velocity will be what? U cos alpha. Okay, because you were suppose you was throwing with the particle, the projecting the particle velocity, you can easily see it is making an angle alpha with the horizon. So you can easily break down this u. You can easily break down as u cos alpha and u sin alpha. Okay, so initially dx dt is what? U cos alpha. So u cos alpha, once you plug it in here, you're getting the value of this arbitrary constant is now becoming fixed one. So dx dt equals u cos alpha. You differentiate it once again, you are getting this one. And again, you are using the initial condition at t equals to 0. That means when it has not yet started the journey, what was the value of x? 0. So here we are getting the value of b equals to 0. So this is x equals to whatever is coming t into u cos alpha. Now let us consider the second equation of motion. So this is the second equation of motion. You can easily integrate it here so as to get this one. And what was the initial velocity along y-axis? U sin alpha. If this is my u, then along this it is u cos alpha. Sorry, along this it is u cos alpha, and along this is u sin alpha. So here it is u sin alpha. So you are putting it here. Once you put it in here, you get the C fixed. Okay, and corresponding dy dt expression comes out like this. You can again integrate it. Ultimately, again, you are getting d as another arbitrary constant, which is easily you can remove by using the initial condition. What was the initial condition? When this t equals to 0, there is no displacement, right? So x was also 0, y is also 0. So y equal to 0, you plug in, you get this expression. Okay. So from here, what was our aim? If we recall back, we are trying to find out the trajectory's expression. So what is our main motive? Remove t somehow. So you have got in equation 8 y expression in terms of t, and some steps back in this equation 5 we got x in terms of t. So easily you can put t equals to x by u cos alpha. So once you use it and simplify it, you are going to get this thing. Now look at this equation a bit carefully, what you are getting. Y equals to, let me just simplify it, what they are trying to say. Y is equals to some ax minus x square, right? Let me just take it out again. Minus some bx square. So easily you can frame it as x minus some alpha whole square plus some beta square, if you may say this thing. Okay, and beta, let me say beta only. So I can just bring it, rearrange it carefully, and this, and also you have to scale it properly. So suppose you get some C here, capitals. Okay, so that means you can put it like 4C by 4, then this thing. Okay, so can you just get the idea? Obviously, it is something I am getting this structure. Y equals to 4a x square. Now, depending on what is the a value, it can be minus here or cannot be minus here. So, depends. He, how is the parabola? First of all, we are getting parabola, right? So, what we claimed before, we are going to get the trajectory as in a parabolic path. We are easily getting it, right? And how is the parabola here? Parabola is something like this. That means here its axis of the parabola is either it is not directly parallel, directly y-axis, it's something, some line parallel to y-axis. Okay, like this, we are going to get the trajectory. So, what is our main remaining task now? You just simplify and bring it in the form of parabola, and then you find out some of the geometrical, geometrical properties from here. What is the directrix? What is the vertex? And what is the focus? Like that. And using those, we try to find out some physical situations, conditions such as what is the latest height, what is the horizontal range. It may cover like that. So let us proceed. You can just easily follow from here because these are some calculations we made. Okay. So as I said, this is the thing which you are getting, then you are just putting it in a proper form so as to get, see, this is the equation you are getting. X minus this whole square equals to y minus something. So this is your capital Y and this is your capital X. So from here, as they have already sorted out, and this covers your A portion. This 4A is the lattice rectum part actually. Okay. So from here, you can easily find out length of the lattice rectum 4A equals to this. And vertex is what? What is corresponding to the x equals to 0, y equals to 0. So x equals to 0 means x, this capital X0 means x equal to this equation. And or rather this expression, y equals to 0 means y equals to this expression. So this gives or this constitutes the vertex of the parabola forming the trajectory. Okay. And this is the coordinates of the vertex. And what else? We can find out the axis of the parabola. What is the axis of the parabola? Vertically downward. Because why downwards? Because minus is there. Right. Y square minus 4x vertically. It is a bit mistake here. They're writing x square minus 4y and y square minus 4a. So x square minus 4a is vertically downwards. Okay. And for the focus, what do we need? X equals to 0, y equals to minus a. So from here also, you can just find out x equals to 0 means against the big x expression. If you equate to 0, you're going to get this small x equals to, that is the abscissa part of the focus and correspondingly the ordinate part of the focus. So this is the coordinates of the focus. And what is the equation of the axis of the parabola? As I said, x equals to 0. So this is your equation of the parabola axis. Okay. And directrix is what? X equals to, directrix is what? Perpendicular to the axis and at a distance a from the vertex. Okay. So at a height above the vertex a, at a height a above the vertex. Okay. So that means here, if this is the thing, this is the parabola. And so suppose this was my axis, sorry, a bit distorted it is becoming. This is my vertex. Okay. So where is my directrix? It is perpendicular to the axis, right? This is my axis. And the directrix is somewhere like this. So what is the distance from the vertex? Height or rather distance from the vertex? It is A. Okay. So it is parallel to the x-axis. That means you are getting here y equals to some fixed. Y is equals to A. Like that. So from there only you can get out or rather find out the equation of the what is A? What A is like this thing, and at a simplification, just a bit simplification, you can get y is equals to u square by 2g as the equation of the directrix. Okay, because if you just remember, a capital A was what? U square by u square cos square alpha by 2g. At a height means what is the height? That is we are measuring from the x-axis, right? It's from the origin. That means from the x-axis we are measuring. So this A plus whatever the height was. So we need to add up these two things. That means at this height, you are getting the directrix. That means at a height of this one on the x-axis. Okay. Now, as I said, some of the physical ideas we need to get a clear idea from here. The greatest height, that means at what point the velocity becomes 0. Okay. So what we need here, see, we are again starting from the equation of motion with respect to y-axis. But here, instead of integrating, what we are doing here, we are trying to find out dy dt is expression. And we know this common strategy, multiply by dy dt and then integrate. We will obviously get this thing. So why we do this thing? Because we need dy dt on the left hand side. Because as I said, for greatest height, what is the condition? Dy dt equals to 0. So once you get this thing, along with the E fixed via initial conditions, okay, so you can just divide it equals u sine alpha initially. So you can easily plug it in, and so E becomes fixed. So you get this expression. So here greatest height is capital H, then what happens? Divide it to 0. Okay, so if you put divide it to 0 and y equals to capital H, so you can easily get out H equals to, you can easily make out what is the H capital H value. This is the greatest height. Okay. And now what is? Particle displacement y vanishes. So let us see what they're trying to do here. Time of flight. Okay. So how much time it requires to do starting from this point. And then you are coming to this point. So time of flight here, as we are saying, you need to find out time of flight, right? So time of flight means what? If you are trying to find out the time of flight, that means you started from this point. Okay. And then you are again reaching back the ground at this point. So what is the total time required? Here set t equals to 0, t equals to t. So we need to find out this t. So what is the condition? Say once you reach the ground, what is the particle displacement? Y equals to 0. So I need to use this y equals to 0. Where? In y equals to ft expression. So what is the ft? Ft already we have derived. As you can see here, this is the ft situation. Let me just scroll it a bit. This one was the ft situation, equation 8 from equation 8. So you just plug in y equals to 0 when t equals to capital T. So simply you will get t expression here. Okay. So the required time of flight also we have got. Achha, last one, what is the required horizontal range? So what is the horizontal range we are meaning here? Horizontal range means you are starting from here. Say suppose this is origin and this is suppose A. So this is the distance along the ground you are actually covering. Your particle is starting from here and your particle is reaching or again striking the ground at here. So this is the horizontal range, right? The vertical range has become 0. As you can see, it started from the ground, it has reached the ground. Okay. In the meantime, it has gone at some height, but again it has then came down. Okay. So the horizontal range, how should we get it out? With the help of the horizontal velocity, which we have got, and also the time also we will use, because the time of flight we already know. So required horizontal range is what is the horizontal range corresponds to displacement along x-axis, right? So what is the displacement along x-axis? You can say velocity into time. So what is the velocity? If you just recall back a bit, along the x-axis, there was no velocity other than u cos alpha. So u cos alpha is the velocity along x-axis. Let me just draw it a bit. So along this, it was u cos alpha. Okay. And you have covered this, or you have rather used this velocity or moved with this velocity for the entire time of t. So what should be your displacement along x-axis? U cos alpha into t. Because if you can just think of also like this dx dt, what dt time, then also you can dx dt for dt time, let me put it here. Okay, then also you will get the dx like that. So this is your horizontal range. Now already you have calculated t's amount, so you can easily plug it in here and you get the required horizontal range for the flight. Okay, so let us stop it.